transforms. So I actually disagree with the name that I gave this in these notes. I give myself a solid F- for that name. I'm going to call this a permutation matrix. Oh, yeah. All right. I give myself a solid A+ for that name. All right, this is, I actually wrote a whole section on permutations. I don't teach it every quarter because we don't need permutations until, really we don't need them until determinants. Do you know, I'll do a quick crash study here. If I did permutations from this set to this set, so a permutation is a bijective map, right? So here's a permutation, send 1 to 1, 2 to 2, 3 to 3. That's called the identity permutation. Okay. So this set actually, the set S3, this is called the symmetric group on 3 elements. This is very, very famous mathematics. This is abstract algebra. No, the S3 is abstract algebra because it gets into group theory. You could take a 3-quarter class that would end in Gauss law theory to prove that quintic polynomials and above don't have roots that can be written as or don't have roots that can be written using cube or nth roots, right? That there's no closed form solution to quintic polynomials and above in the same way there is the quadratic formula, right? That's called Gauss law theory. That's a very, very famous thing. I don't want you to worry about this, but the funny thing about linear algebra is that all of our theory depends on this other stuff. This is what kills me about mathematicians, right? You ever seen a math book that's written? You don't need any outside math in order to understand this book. It's like, yeah, theoretically I could put my son in the driver's seat of a car and he'd be fine. Theoretically, right? So the reason I'm going to say this is I want you to know where this name comes from. So this is called the identity permutation. How many different ways are there to map a set of 3 elements to another set of 3 elements? Well, yeah, there's 6 of them, right? It's, 3 choose 2. Okay, so now we've got 1, 2, 3, 1, 2, 3. You could do this one too, right? Okay, you could do 1, 2, 3, 1, 2, 3, and you could do this one. And then you could go 1, 2, 3. These are now called cycles. There's a nice proof of a fun fact later in the course that comes from cycles. So you could go 1 to 2, 2 to 3, 3 to 1. And my claim is that's a different permutation than if I went 1 to 3, 2 to 1, 3 to 2. Okay, claim. These are called transpositions. Nope. That's a transposition. That's a transposition. That's a transposition. Next claim. I can write all permutation as compositions of transpositions. Composition. Every one of these is a function, right? What does the chain rule say? The derivative of the composition of functions is the derivative of the outer function times the evaluated of the inner function times the derivative of the inner function. I can decompose every single one of these as a set of transpositions, and that's true for all permutations. It's a non-trivial fact. We're not going to talk a lot about this until we get to determinants, and then we're going to need it, and somehow we'll pretend that you don't need it to make ourselves feel better about requiring you to take this class without the prerequisite knowledge. Okay, here's the claim. I eventually want to map 3 to 1, right? So here we go. What if I went like this? Sorry. Yeah, that works. So look at that composition there. Just follow your nose. Okay, what does 1 go to? 2. What does 2 go to? Just follow it. Dunk, dunk. Yep, and then 3. Okay, so claim. This function right here is the composition of 2 other functions. It's the composition of this function and that function. That is true for all permutations. I can write all permutation as the composition of transpositions. In other words, transpositions generate the space of all permutations. I don't want you to worry about that. I'm not going to ask you to worry about that today, right? But here's a claim. When we talk about transposition matrices, we're going to be doing one thing. What does every single one of these permutations do? Change 2 elements and leave everything else alone. It's not it is a subset of permutations. What do permutations do? They're bijections. Everything in the domain hits everything in the range. Everything in the domain is mapped exactly once. So they're onto and one-to-one. So permutations do that in many, many different ways, right? But there's a subset of permutations that are called transpositions. Those are very, very special subsets. What do transpositions do? They leave everything alone except for 2 elements, and those 2 elements, what do? They switch them. That's it, right? And then there's a famous result that we're not going to prove this quarter that we should prove before we get into this class, that transpositions generate all permutations. We'll get there later. That's not a trivial fact. Could you guess what transposition matrices do? They change 2 columns, or they change 2 rows. That's why I call them transpositions. There's something called permutation matrices, which is the generalization of that, but that's where that name comes from, and I'm actually proud of that name. I'm not proud that we require you to take this class without this knowledge, though. That makes me angry. All right, so here we go. Let n be an element of the natural numbers. If we say, let's make sure that I does not equal to k, and define the transposition matrix PIK, well, I don't know if I like that definition. I'll do it 2 different ways. How about this? We'll call it IN. Now I see why I use that definition. So let's go. J goes from 1 to n of EJ transpose, but J is not allowed to be K or I. And then what we're going to do is we're going to add the appropriate non-zero locations onto this thing. Couldn't you guess? What did we say transpositions were? Formally speaking, what's a transposition? Flipping something. Could you guess which ones are flipped? I and K. So let me ask you this. Just without writing it down, let's see if we can guess what this will be. It's going to be a matrix. What does EJ transpose look like? It's going to be a matrix unit. Every single element of this thing is going to be 0 except for a single 1. Where is that single 1 going to be located? JJ. I'm going to run from J goes from 1 to J equals n. Imagine there's no other conditions on that. What is this sum? Give me an I, give me a D, give me a... It's the identity matrix, right? If I was allowed to go from J equals 1 to n, and I have the matrix units where the diagonal entries all have 1s, everything else is 0 in the jth entry, right? That would be the identity matrix. But then I say to myself, yeah, by the way, rows k and I are going to be all 0. I'm not allowed to add 1s in row k or row I. Then what do I do? In row I put column k, and in row k, I put column I. So what did I do? I swapped them. Okay. So another way to write that, the fact that you can see that, I'm telling you right now, there are PhDs who study the subject that might not have ever looked at this material. Or PhD students anyways. Most PhDs would be like, yeah, this is trivial. All right. So the claim that we're going to do, another way to think about this, let's think about what you would have to do to swap rows I and k. Okay, so in rows I and k right now on the identity matrix, in row I, which entry of row I of the identity matrix is non-zero? The main diagonal entry, right? So I would probably want to take that main diagonal entry and do what to it? Eliminate it, right? Because it's not allowed to be 1. I want nothing in that row, right? The moment that I eliminate row I, what would I do? I would replace row I, instead of having the ith coefficient be 0, I would have the I kth coefficient be 0, right? So I would say, okay, let's go ahead and add the I kth coefficient. So in row I, this one's going to be non-zero. So now that would place in row I, it would place a 1 in column k. How would I get rid of the other one? First thing I would do is I would get rid of column k. And then what would I do instead? In column k, I would want to add a copy of row I. That's another way to define that. These two are identical, right? And in fact, do you notice right here? That's this one, and this one together. What did we say about the identity matrix? If I wanted to write the identity matrix as a sum of matrix units, what did we say about IN? It's the sum from j goes from 1 to n of EJ outer product EJ transpose. Now if I take away EI transpose and I take away EK transpose, what happens? Yeah, that I literally just take away those two sum ends of that n sum and sum, and I'm left with this thing. And then I add the other two. Okay, so let's go ahead and check what this will be, and we'll do it step by step, right? Yeah, of course. One of the greatest gifts that a professional mathematician can learn is how to generate their own examples. Should we try it? But seriously, if you give me a definition in a few hours, I can come up with any example for that definition. It's not a trivial thing to do. So let's go ahead and do this. Give me some numbers here. So we'll call this example 3.4.6. Do you want to use my example or do you want to use your examples? Yeah, let's use yours. Because you're just so much cooler than I am, right? Because you're breathing. I am breathing. It's just anybody that breathes I generally think is pretty cool. At least cooler than me, right? Thank you. All right, give me some numbers. And maybe we'll... Katya, could you look at your watch again? Okay, what's n? Yeah, it's a lot of pressure, huh, when she looks at her watch. Like, damn. All right, n equals 4. Give me, what else do I need here? Do I need a c? Do I need a constant value? No, so give me some i's and k's here. 3 and 4? Okay, p. Well, let's not do 4 because we don't want to cross-pollinate here, right? 3 and 6. Oh, that's crazy. Oh, 2 and 3? All right, let's do 2 and 3. How big is this matrix? 4 by 4. Which of these formulas do you want to use first? Do you want to use this formula first or this formula first? Top one? Okay, that's cool with me. So j goes from 1 to n. So I guess what we should do is we should actually make the explicit connection, right? PIK. This is the sum from j goes from 1 to n of EJ transpose, where j is not allowed to be I or k. Okay, so let's go ahead and take a look at that. This is going to be the sum from j goes from 1 to 4 of EJ transpose, except j is not allowed to be what? 2 or 3. And then what am I going to do? I'm going to add EK EI transpose plus EI EK transpose. And I almost want to go back to Shahand, what is this dot right there? How big is EI? Yeah, there you go. Very nicely done. Very cosmopolitan. All right, what about this one right here? Let's go real slow here. So I is equal to what? 2. K is equal to 3. So let's just fill that in. What's this one? E3, E2 transpose plus E2 times E3 transpose. Okay, let's go ahead and run. Where do I start my lower index here? 1. Is there any condition that J is not allowed to be 1? So what's the first one I write? E1, E1 transpose. And then if I was a normal sum and I didn't have constraints, what would I do next? J equals 2. Am I allowed to do J equals 2? Nope, so then I increment by 1. What's the next one normally? 3. Am I allowed to do 3? Nope, so I just skip that. What's the last one? E4, E4 transpose plus E3, E2 transpose plus E2, E3 transpose. Now what? Okay. What do we say about our ability to skip steps because we're tired? That's right. That's right. I mean, generally take a break if you're really tired, right? But if it's not break time, then work. Yeah, I guess it's playtime too, but play is different than breaks, right? I'm running out of space here. So I give myself a nice F for boards management in this case. So this means P23 is 1, 0, 0, 0, 1, 0, 0, 0. Now what? 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0. Nicely done. And finalmente. Y entonces, all right, let's go real slow here. Remember, did we say we like rows better or columns better last time? Columns. So then this time maybe we like rows better. So now what we're going to do is we're going to take scalar multiples of the rows and then put them in the appropriate place. So what's the scalar multiple we're going to put in row 1? 1 times that row. 1, 0, 0, 0. What's the next one? Yeah, those are kind of the most beautiful rows that you'll ever see, right? Okay, now what? Scalar multiples of the rows. The first 3 rows will immediately be 0. The last row will just be a copy of that row vector, which means what's that matrix? Question, can you see this right here? Can you see this right here? Where is that right there? Those two sums, where is it? Boom. Okay. Can you see this right over here? Can you see this in the bottom thing? Yeah, that is the identity matrix. So I guess we should write it out, right? 1, 0, 0, 1. It's the identity matrix where we've canceled out what? We've canceled out 2 spots. Which spots do we cancel out? The ith spot and the kth spot. In this case, I was equal to 2 and k was equal to 3. And now what? All right, we just like rows better. Now we should like columns better just so we can flip-flop a lot, right? Good politician. All right, so what do we do to create this inner product, or outer product, I'm sorry? We take scalar multiples of the columns and then place them in the appropriate column. So in the first column, what scalar multiple are we going to take? 0. So what happens? 0. 0, 0, 0, 0. Now what? 0, 0, 1, 0. Now what? 0, 0, 0, 0. Now what? Okay, and then finally, let's do it again. Chris, maybe you can help me on this, and not that Chris, but that Chris, right? Okay, so we're going to do it by columns. To form the first column, we're going to take a scalar multiple of this one. Which scalar are we going to use? 0. What vector is that? Yeah, the most beautiful vector ever to exist. At least from the standpoint of thinking, right? 0, 0, 0, 0. Then what?
Everything will be 0, so there'll be 1 at the third column, and then, yeah.
Awesome. Okay. Can you see this? Well, first of all, what is that? Now I want you to use the word transposition. Not yet. The transposition matrix is the sum. Okay, remember, what's a transposition in terms of permutations? What's a permutation? Permutation is just taking a bunch of elements and rearranging them, right? Yeah, a transposition is a special type of permutation. So what does a transposition do? Everything stays by itself except for a single pair, and that pair does what? Swaps. Now use the word transposition on this matrix right there. Yeah, it represents a transposition of the second and third rows of the identity matrix there, and then everything else is 0. What happens when I add them? I get basically the entire identity matrix, except in the second and third row, I've swapped them.
Can you also think of it second and third column?
Sure. Just depends on what, yeah. Why? Because the identity matrix is symmetric. Oh, shit, Jeff, slow down.
Did you say though, usually people column?
Not always. I said that we tend to write column vector first, but we will see. We're actually setting up for Gaussian elimination right now. We're doing this, in the space of matrices, we'll be getting there. And when you're multiplying, yeah, so we'll get there.